In this lesson, we're going to learn about two theorems. One is called the factor theorem, and one is called the rational roots theorem, which really is a special case of the factor theorem. The factor theorem is based on division and the division statement. P equals dq plus r is one way it's written, meaning dividend comes from divisor multiplied by quotient plus remainder. If I consider functions, I can rewrite the division statement this way. P of x, or f of x, a polynomial in x, is equal to the binomial linear divisor x minus a multiplied by some quotient plus a remainder. If I substitute the value a, I get the remainder. This is the remainder theorem that we've already learned about. Now here's what's new, one extra consideration. If p of a gives the result of 0, that means the remainder is 0. Therefore, I found a factor. When there's no remainder, we have a factor. So x minus a, the linear binomial, is a factor of the polynomial p of x. There are two ways now to go about getting factors. One, we can use the remainder theorem looking for r equals 0, which is really the factor theorem. So the factor theorem piggybacks on the remainder theorem. Or we can use synthetic division, which has been discussed, and look for a remainder 0 in the last element, recognizing that when there's a remainder 0, we have found a factor. We're going to look at an example here and solve it by both methods. So the question is x plus 2 a factor of x cubed plus 6x squared plus 11x plus 6? First method. What I'll do is I will consider the function to be that cubic, x squared, 6x, x cubed rather, 6x squared, 11x and 6. So by method 1, I'll be testing the function for the value negative 2, which is negative 2 cubed. Watch your bracket and order of operations. Negative 2 gets squared. I've got negative 2 multiplied by 11 and a 6. So this is going to be 24 minus 22 plus 6, which is negative 30 plus 30, so it's 0. So yes, x plus 2 is a factor because the remainder is 0. That's the factor theorem. Simple as that. The other method that I could use would be to use x plus 2 with detached coefficients. So I'm just going to keep the 2. I'm going to write the synthetic division with coefficients 1, 6, 11, and 6, representing x cubed, x squared, x, and constant. I'm going to perform the synthetic division operation, which we've practiced and discussed before. And the fact that this last element is 0 as a remainder means x plus 2 is a factor by the other method. Now, furthermore, one good thing about synthetic division is that you get x squared, 4x, and 3, which is actually the quotient, which is factorable further to x plus 3, x plus 1. So, if we were to test, and I'll leave this with you to do, f of negative 1 should give 0 according to the remainder theorem and factor theorem, and f of negative 3 should also give 0 according to the remainder and the factor theorem, because the remainder will be 0 because they are factors. Now, I'd like to note something here before I move on to the next theorem, and that's this, that the dividend we had, the cubic, is equal to these three factors that I found in this case. Not everything's going to be fully factorable every time, but this one was. And notice how the number 6, the constant, is developed from 2 times 3 times 1. So it suggests a procedure for doing your testing of your factors. If you weren't given a factor, like x plus 2 or x plus 3 or x plus 1, you can get a hint of what to do by looking at that constant term 6 and thinking of its factors. The factors of 6 are plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. If I test any of those numbers in the function and get a 0, I have found a remainder 0, therefore I found a corresponding binomial factor. Now, sometimes it's not quite so simple as this, and that's where the rational roots theorem comes in. So you'll notice that I've described a generic polynomial as we've talked about previously. This time I'm setting it equal to 0 to make an equation because I'm trying to find roots. Now, Possible roots for this that we already are aware of, according to what I just finished discussing, are the factors of a subscript 0 or a naught, the constant term. But in addition to that, there are other possible roots that are rational roots, meaning fractions. They're formed from any factors of a sub n divided by, a sub 0 divided by a sub n, the leading coefficient. Here's an example to show what I mean. I'd like you to solve this cubic polynomial equation. Notice that the leading coefficient is not 1 this time. I'm going to let that be f of x. Now, if I look at the constant term of 1, the factors of 1 are plus or minus 1. So let's try substituting 1 and negative 1 into the function and see what I get, because that's how I work the factor and remainder theorems. So substituting 1 yields 2 times 1 cubed, 15 times 1 squared, 9 times 1, and 1, which is 2, 15, 9, and 1, and is definitely not 0. So I don't have x minus 1, which, x plus 1, which corresponds to that. No, minus 1, gosh. X minus 1, which corresponds to f of 1. Let's now try f of negative 1. Substituting into the function, we're going to have negative 2, I'm going to do a little mental math this time, 15 minus 9 plus 1. This is negative 11 plus 16. This is also not 0. So I can't find factors using the factor theorem using the constant term 1. So now let's try the rational root theorem. Let's recognize a subscript 0 has factors of plus or minus 1. A subscript n has factors of plus or minus 2. So plus or minus 1/2 is a possible consideration. Let's substitute negative 1/2 in. Now, I'll leave you with this question to answer for yourself. Why am I not even trying positive 1/2? Excuse me. So we substitute negative 1/2 in. Like that. And we simplify. This is negative 1/8 times 2, so negative 1/4. This is going to be positive 15 quarters. This is minus 9 quarters, but I'm going to write it with a common denominator, and I'm going to change 1 so it has a common denominator as well. So I have negative 19 plus 19. I have 0 over 4, or 0. So what I just found out is that x plus half, or another way to write it is 2x plus 1, is a factor. Excuse me. I can set about finding other factors now by using synthetic division. So I'm just going to use the plus 1/2. I'm going to detach the coefficients and write those down, and let's carry out synthetic division. That confirms the 0 remainder, that x plus half is a factor, but notice that I used factor theorem even to find it, to have an idea of what to do. Now, there's another little trick here. This relates to the quotient, but it's not actually the quotient, because the actual factor is 2x and 1. And what I looked at was x plus half, which is half the size of the factor that I actually need. So that leads to a quotient that's twice as large. So I need to divide the quotient by 2, leading to x squared 7x plus 1. So what I've now found is that 2x cubed plus 15x squared plus 9x plus 1 that I was given is equal to 2x plus 1, the first factor I found, multiplied by x squared 7x plus 1. And if you check, multiplying out the right side or expanding, 2x times x squared makes 2x cubed. If this were a 2 in front, I would end up with 4x cubed, which would be too large. Now, this is not factorable. You can check that that's true. Factorable is what I meant to write. And so, what I'm going to need to do to resolve this trinomial is I'm going to use quadratic formula. Negative b plus or minus b squared minus 4ac all over 2 times a which is negative 7 plus or minus 49 minus 4, 45 over 2. 45 has a perfect square of 9, so I can rewrite this as negative 7 plus or minus 3 root 5 over 2, which is irrational and can't be reduced any further, could only be approximated as a decimal. Finally then, the roots are negative 1/2 and negative 7 plus or minus 3 root 5 over 2.